So, hi everyone, welcome to the Bangalore Theory webinar series. So this week we are excited to have Dr. Sandeep Manjanna as our guest speaker. So Dr. Sandeep Manjanna is currently a founding faculty at Plaksha University. So prior to this, he was a postdoctoral fellow at the University of Pennsylvania, and he finished his MSc and PhD from McGill University. His research interests include multi-robotic coordination, robotic active sampling, machine learning, and reinforcement learning. And Dr. Sandeep's PhD thesis was awarded the CIPPRS, what is it? John Barron Dissertation Award in Robotics for its impact in robotics in Canada. So today he has kindly agreed to give a talk titled Multi Robot. Yes.
Okay, can you?
Right.
It's okay, no worries.
No, I got it. Multi-robotic planning strategies for spatio-temporal sampling. So yeah, or just
So the introduction, yeah. This is the most hard part to get to learn. I feel embarrassed throughout. Yeah. So I'll be talking about some planning strategies for multi-robot systems for doing spatial sampling. So here sampling refers to data collection, or like it can be either any water quality measurement, air quality measurements, or it can be image data also. So also along with that, there are works where I have also done physical water samples or physical samples from the environment. So I would like to start with this quote from Leon Megginson, which actually says like any species for its survival, it doesn't have to be the strongest, but it should be more adaptable to any changes in the environment that it's staying in. So my PhD thesis has PhD research and also during my postdoc research, I have mostly concentrated on developing algorithms for adaptive planning for adaptive behaviors for robots. And initially, I started working with gated or legged vehicles where I was working on gate adaptations based on the terrains. And like this is an amphibious robot that we built in the lab, which actually goes underwater and also works on terrestrial environments. And basically, the task was to identify when you have to swim or adapt your gates according to the environment you're walking or swimming in. And later, I switched gears into more multi-robot sampling strategies where I was looking at more environmental monitoring style of things, where I started with water sample collection. You have a sampling robot and you have an explorer robot, which actually maps the water quality, and sampler robot goes and collects water samples for biologists and ecologists to analyze in the lab. And continuing on that, I worked on algorithms on multi-agent orienting algorithms and spatial sampling algorithms. And this is just an overview of a couple of things that I've worked on. And basically in today's talk, I'll be talking mostly on selective sampling or like adaptive sampling strategies. How do we collect this data, or where do we collect this data? How do you decide where to go and collect this data? That's the topic for today's talk. So if you think of some of the applications, where would the data collection or like monitoring systems or surveillance systems be helpful? Like if we have more data, can we better understand the forest fires, why they are spreading or how they are spreading, or things on can we track the infestation tracking in agriculture, or also localize pollutants coming into a lake or a river or a nala, like how one of the projects we are trying is in Mohali. There's actually a river stream, but it's become an nala now. There are many in Bangalore also, I know of like that. So mapping and monitoring those environmental systems. And unfortunately, you can't see anything here, which is a very beautiful picture of coral reefs on the left, but then there is a bleaching happening. Sorry? Yeah, that's what is happening, but they're getting back, is what I heard recently. So basically, coral reefs are getting bleached. That's the white parts that you see here, and then they're going to die after bleaching. So mostly I work in marine environments and freshwater environments. So mostly the examples I'll be taking are from marine environments.
So we
Yeah.
more pedestrian question to begin with.
Yes.
Like why automation is sort of like a lot of this is important enough that humans can, but it's like it's the toxicity of the environment or the hazard, the fire, nala. Is that the reason you want robots? Like
Also, like basically, if we are, let's say I'm monitoring ecosystem like coral reefs, right? And right now, I have collaborators from marine biology who are actually like they have students like they pick a small spot and they mark like 1 meter by 1 meter cube, and there's a student going swimming and taking a picture every day. I don't think that's the way it should be done. Our students should spend 5 years doing just taking pictures. So that's one thing. Like it's very hard work for humans, and also the environments are not always easy to get to, and they're dangerous to get into. And also the precision that you can get with the robotic system would be much higher than a human system. But then it's not like replacing a human, but if you human can give inputs and robots can execute, that's what we're looking at. Yeah. So currently, can additional data help? Like currently, how all these data are collected? Like satellites, of course, we get a lot of data from satellite systems, but the resolution is pretty low to make any real-time adjustments or like real-time changes that we want to bring in. And then there are occlusions, of course, and the time it takes for revisiting is very low. So time takes for is longer, so revisit time is low. And other ways are basically stations, ground stations, and then there are buoys like sensor buoys in the oceans doing this monitoring, but they are very localized and they are very short range of data that they collect. So if we can deploy robots or multi-robot systems that can actually survive or do persistent monitoring of these environments, then we keep getting updated data every day or within every 1 hour updates, and then you can build better models using those data. So some of the assumptions that we start with, most, yeah.
surveillance. That it's this.
It's based on interest. Like
Okay.
I was kind of interested in auto monitoring, and the lab I was in basically was interested in that. So that's how I got into this. Yeah, I haven't looked at that one, but I have looked at search and rescue parts, not the security.
But I would imagine like, those things. Security application, the target itself is somewhat moving and adversarial.
Yeah, the adversarial behavior doesn't come into picture here.
Yeah. That
So
does,
yeah,
yeah.
there you need to do more tracking or like you're chasing the target, but here you're not doing that. Yeah, but kind of you're still chasing the hotspots,
Yeah.
which you're building models for. You can apply similar ideas, but not exactly. You need to still like make it. You have some like game theory coming in there, right?
Yeah. Like you're seeing this hotspot are slowly changing.
Yeah, hotspots are changing. Like it's a dynamic
Slowly changing.
compared to the robot speed. Yes, that's what another assumption we make when we think of spatio-temporal processes. These temporal changes are slower than what robots can track. Or else there's no there's no point in deploying robots there. Or else I would just put sensor stations and monitor it. And basically, uniform sampling of these locations is inefficient. So, for example, if we think of coral reef monitoring, and coral reefs are kind of these coral heads that are spread across, and doing a complete coverage or uniform coverage of such a region. Now, like I have audience partially arranged, right? Like if there's a coverage system which is covering everyone or like serving tea to everyone, and then going row by row, then you're wasting a lot of time in just going to seats which are not occupied. So instead of that, we should be more adaptive and seeing at the people, like if you can observe, like there are clusters of people. There are some sitting alone, but then there are clusters of people. So that information you can actually take into account and decide where to go. So we propose adaptive and information-driven robotic path planning algorithms. And in this context, as I already mentioned, sampling refers to collecting data or collecting images, or also taking physical samples. So one example I already mentioned is, this example comes from mapping the coral reefs or collecting data for coral reefs. The idea here is the data collection is happening from a surface vehicle. So wherever the regions are shallower, those are more information-rich regions, and it's deeper than 20 feet is what we consider here, because the visibility goes bad, and then it's mostly sand at that depth. Okay. So that's another assumption for this particular application. So I'll start with the first initial selective sampling that we started with. So we start with zero information about the world, and you run some pilot survey. So let's say 4 transects, and you collect some data, and then you fit a Gaussian process model to it, and you generate the field. That acts as your prior. Like now you can use that as your prior to decide how do I go about sampling this whole world, right? So that is given as input to the sampling algorithm, and sampling algorithm generates these locations where the robot should go, and also it generates the path that the robot should take. And as and when you're actually collecting more and more data, you're updating your GP model, and you're generating new priors to the robot to cover. And this is fed back as a reward map to the system. I'll talk about what is the algorithm in the next few slides. Any questions on this?
So you take a Gaussian for your prior just for like because of natural process.
Yeah, most natural processes have like Gaussian distribution, and then they also have spatial correlation. So that comes through with a mixture of Gaussian or like Gaussian processes. Yeah, that's how it is.
It's too much variance. The Gaussian reality could be there, starting there.
Yeah.
Maybe your model starts from here. Like,
you need to tune your variance, of course, based on the application.
In the peak of the
Yeah. I didn't get that. Like, why?
So I guess like more or less like more.
I'm guessing, right? Where it starts.
I mean, the prior is coming from your initial pilot survey, right? Yeah, the pilot survey gave me the prior,
Yes,
and I'm starting with that. Yeah. I'm not starting with like uniformly unknown. Yeah. Okay.
That is somewhat of an interesting question.
Yeah. How do you get the prior? Or how close the prior is? That's what we were talking about. Yeah. And there are different ways of priors I've chosen in later applications. Like you can use the satellite image, or you can use, if it's capturable by RGB, then you'll use a drone image or something. So we modeled the sampling problem as a Markov decision process to begin with, and we start by approaching it with value iteration. But I'll just go through like the modeling, the sampling as a MDP itself. So set of states is basically, you listed as the word, and every grid is a state of the robot. And then robot has a start position that is given, and then robot has 4 actions. In this example, it's up, like northwest, east, south. Yeah. And the transition function is known. We assume that the model is given to us. Transition is nothing but if you're in state S and take an action A, and what is the probability of reaching state S prime. Okay. And we assume that it's given to us with some probability it will reach to the cell next to it, or above it, or below it.
So the states are just the grids in your.
Yeah, states are just the position of the robot in the grid like coordinates.
So I mean, the transition model is I mean, that's very okay. Because
it's a probabilistic model, like with probability 0.5. If I take an action right, right, and with probability 0.5, I'll go to the cell on the right. But with probability 0.3, I may be going up, or I may be going down.
That's because of the
randomness in the robotics and control systems, or the environment, or things. questions? If you know that there's no disturbances and no errors in your system, you can also have like deterministic, right? Yeah. Yes, the model can change, but in here we are making assumption that model is same model. Yeah, we are not taking the sensor measurements to rebuild the model. You can change the robot model, like motion model, according to your measurements. Yeah. So that's the reward. I didn't speak about the rewards. So rewards is basically coming from your prior, which you already computed. So you're just taking the prior as your reward map, and then you're using that to actually come up with value functions. So this is basically a transformation of Bellman equation, where you want to maximize the total value that you achieve by taking some action that you take A. Okay, so we are maximizing over action A, and what action will maximize my rewards? What this action, this particular equation is performing. Okay, this is a vanilla value iteration function, and basically there's one problem is in sampling models, revisiting the location is not useful because that doesn't give us any additional information. Thinking of it as just spatial field, right? If we think of it as just spatially distributed, not temporal, revisiting is not a good idea. But MDP doesn't take care of that. In MDP, revisiting keeps giving you the reward. So one thing we tried starting with is basically doing something called one-step MDP, where you take an action and you say your word deinitialize, and then you run your value iteration again. This can be done just locally. You don't have to run it for the whole space. Okay. And some of the key advantages of this approach were basically it's an anytime algorithm that you get like however long the battery is running, you can guarantee that you have best that you could have done within that battery life. And varying resolution sampling is based on the rewards that you're collecting. If the rewards are, if you can pick up a threshold, then you can decide what should be the resolution of my action space. So if my reward that I'm getting is lower than some threshold, then I'll say like I have covered bigger region than what my grid size is. And then it's sorry. Not exactly. I haven't done that analysis yet. So that's the part there's no optimal value you can pick. So one of the problems is orienting problem, which comes closer. But here I'm not planning based on a budget. Here I'm planning for any time, right? Like I have to take a good action. My battery can die anytime. So every time I need, it's not.
What's the production?
So instead of going to the maxima directly, you want to take a path which guarantees that within the next few steps, whatever you're taking, you're collecting the good rewards on the way. You're not just targeting the highest maximum reward.
Like, as we pose it this way, is it useful to think of like a model where there is a single optima unknown, but there's an optimal that you're trying to compete with? Like kind of going from like a RL version of the problem to a more like a optimization, like unknown with stochasticity because you don't know the exact rewards and all that. But nonetheless, like,
yeah. Considering the prior itself is your actual reward.
Yeah.
Yeah. One way is basically like the orienting could come for help, like here, because now you can actually choose these maximum locations as your nodes.
Yes.
And now you can plan your path according to orienting problem. But again, the difference is basically like here in this one, I'm not considering any budget, right?
Yeah.
So it's not thinking like, okay, I have 10 steps, I want to maximize within that 10 steps. That idea is not embedded in here. That would be the case in oriented problem. So, sorry? We are trying to optimize the rewards that from the prior whatever rewards you are collecting. That's what we are trying to optimize, like maximize. On. Maybe I'm not getting your exactly.
What we the gradient kind of ascent as well. Where you pick like the from a current state to move to a state that gives you the possible likelihood. What does reward mean? So
Reward is basically reward is mapped to your underlying measurement that you're making, right? Like let's pick the coral reef as the example. So reward you're getting is every time you visit a location, your prior says, okay, this should be at a depth of 2 meters, but then you measure it as like 3 meters or something. Then your reward is actually lower than what you expected, right? So your reward is coming from your actual measurements, like you're mapping your measurements into the reward.
Yes, there's a series of measurements you're making over time.
Yes.
It's like some of all these things that you're trying to.
Yeah, you're taking you accumulate the rewards over your whole trajectory. Yeah. The sum is what you're trying to.
So if I look at the equation again, please.
Yes.
Yeah. So
Yeah.
here T is the dynamics, it's the motion of the
It's the
RS is the prior, it's the rewarded state R that you're
rewarded state. Yes. Yeah.
yes, given to you. Like
Yes.
as a prior.
You know what is the
Right. And VK S prime is your like your current estimate of how much you'll be able to gather
starting from S prime. Yeah. This is basically recursive algorithm, right? Like we are actually saying like if I was to start in S prime, this would have been my value. So that's what.
Gamma is just a standard term.
Yeah, gamma is just discount factor. Yeah.
You are like in some sense like a dynamic program locally.
Yeah.
Or,
I mean, value iteration is one of the ways to implement dynamic programming.
but yeah, the catch is like a standard MDP revisiting will not help.
Yeah, that's the difference.
We have some kind of soft budgeting, right? Because of the discounting that we have, essentially. Some kind of
Yeah, using the discount factor, you can actually control that. Yes. How far the rewards are useful for you. Yeah, you can control that. Okay. So one thing we also observed is basically it was much easier to tweak the reward map based on the external measurements. Like if I'm able to actually measure the wind when I'm running the boat, if I'm able to measure the wind, then I can actually change my reward map such that it should encourage only taking the actions which are parallel to the wind instead of perpendicular to the wind, something like that. So we did try those experiments and it was pretty helpful. Like these were very good features, but I'll come to the limitations in the next 2 slides. Yeah.
So the fact that you have a Gaussian process actually does not matter here. Because I could have given you any prior and just use RS and in some sense you've discretized away that.
Yeah, we are not using it as continuous word. Yes, that I agree with that.
Or
yes.
Gaussian. I mean, just some numbers.
Yeah, any prior, whatever you give me, it can.
And I can give you any RS for the grid, for every S and RS. And also the fact that it's actually a very well structured, it's actually just a plane. It's just rolling. So this might help in terms of like running the algorithm. But as such, like, this has not been exploited, let's say, to argue.
The fact that there are no obstacles or
no, the fact that like you haven't tailored the value iteration algorithm for these. Say this
no, we are using just a
it is only 4 neighbors.
Yes. Yeah.
The equation is not correct.
But one way you can actually change that is also like you can run the same algorithm in street network where you have this distribution, but then you have street network where you can't go into a building, right? So there you actually change your reward map accordingly. Like you have the map of the world. There your rewards will become like you start penalizing the robot if it takes actions going to the buildings. So that way you can control that. But it's more engineering, like you're engineering the reward map.
Just to sort of repeat what Saurabh was asking, like if I give you two algorithms, this is like a value creation algorithm. I give you some other algorithm. The way you compare that, say that this algorithm one is better than algorithm two is based on like you would look at the entire path trajectory and then say which one has accumulated more of it.
Yes.
And that
Yeah.
That would be your ground truth for comparison.
Yes.
The optimal would be like a path that does this the best.
Yeah, optimal will be the path that it does the best, but
Yeah.
I haven't worked on that optimal algorithm. Like I don't have one. Yeah. So that's just to show the deployments in the field, and so also in simulation. And, yeah. Anyway, trust me, these two look similar. And then like this is basically for doing like complete. Yeah, this is complete coverage, which took like 2.7 kilometers of travel of the boat, and then the other one you can look at my. Maybe you can join the call. That is much better of the Teams call maybe. Yeah. So here with just 1 kilometer of travel, we were able to capture a lot of information of the depth map and build the same exact depth map on the with a limited travel. And on the right hand side, I'm plotting which one has better information, like more number of good visual images. So, for example, if the application is for marine biologists to look at the health of the coral reef, they don't want to sit and watch the images of sand, right? You want to collect more and more images of the reef. So the idea here is like with our algorithm, we were able to actually get more and more good images with longer travels. Yeah. So there are two limitations. One is not scalable, basically because of this repetitive value iteration that you're running. If you want to scale it to a large scale application, then it's not easily scalable. And another limitation is basically if you have, I don't know, there's some colors that don't show it. Sure.
Yeah.
Okay. Because this looks pretty nice. And so this is for theoretical computer science presentations only. Sorry, what was the question? Why doesn't it scale? No, if your grid word is increasing, then you have to run your sorry.
Quadratic is also not.
Yeah. And also actions here we have very like made it into very minimum 4 actions, right? Like, but in robot space, like you have more continuous actions. That's where, sorry. I mean, if I'm traveling, here my heading is going straight, then I have all the degrees, right? Like I can discretize into many, like 1 degree at a time, or I can go to half a degree, or like if I want to do much smoother trajectories. This will come into picture when you're working with drones, right? You can't actually stop and take an action and stop and take an action. That will become more hard because your drone will actually has a momentum which will kind of push it forward. Here we don't have so much, like with the boat, it's much easier. Yeah, here it was just 4. Yes. Yeah. But I have some examples where we do try like 3 actions like 45 degree right, 45 degree left, and just going forward. And the model, it works the same. That doesn't change, like the implementation.
When you say scalable, it's both in terms of time and space.
Space, yes. Yeah. To get a solution in real time for the robot to execute it. Yeah. And another one is also like the concept of this changing rewards or non-stationary rewards is not embedded in the value iteration algorithm. So in this example, it would think like if I go to the reward 10, I can keep reaping the benefit by just visiting and coming out and going in and coming out. But then we want to actually go to a region where you have more number of 5s instead of going to 10, right? So those are 2 limitations. And how do we try to address them? Is basically one is we went with non-iterative approaches like Poisson gradient, where you take sample n number of trajectories and then execute them, and then you update your parameters accordingly. And then another thing is also like we address the problem, the second limitations by actually aggregating state spaces or coming up with feature space which actually aggregates the information instead of considering every grid as separate state. Okay, so I'll just briefly go through the algorithm for using policy gradient approach here. So the idea here is we have this policy gradient theorem algorithm that's actually learning a set of parameters based on the number of trajectories that it samples. Okay, so just to show some math there, m is the number of so j theta is your total rewards that you're collecting or total value that you're collecting over time, and theta is the parameter that we are actually optimizing. So theta will be updated based on delta j theta. Okay, and m is the number of trajectories. So you sample m number of trajectories and roll out them, and then you decide like what is the value I'm getting from rolling out each of those trajectories, right? And once we do this on different input data, so this input training data can come from satellite images, it can come from mixture of Gaussians, like if you're just doing some Gaussian modeling, or like if you know that distribution is something with mixture of Gaussians, then you can train with any synthetic mixture of Gaussians. And then you're just running your algorithm on that, training your algorithm and getting the theta values. And once you're in the field, you take the actual score map for that particular field. In this example, we are taking the aerial image of the reef, and then we are using just some image processing to get the score map on that based on the colors. And we are giving that as input to the learned policy gradient system, right? And what will that do is like based on the parameters that I have learned and known current state, I can tell like what should be my pi. Pi is the policy. Policy is nothing but a set of actions. So it will tell me like what is the probability of success if you take action to the right, or what is the gain that you'll get if you go to action on the top, right? So I'll talk about these two equations again in the next two slides. Let me skip here. I'm just telling like what is the policy and what is the.
So just to understand,
Yes.
Robot this matrix of RS or RS. Like for every state, you'll give it this number RS and expect that the robot executes this maximization every step.
Yes.
Keeping like the VK, their VK plus that.
Yeah.
Value. So it is now what you're seeing is instead I'll use my prior, come up with this function pi, which for every state tells me like what I should do in there.
What action should I take? Yeah.
Okay.
Because that's what you're learning in your training phase.
Yeah.
The theta. Yeah.
In some sense, you're giving it a path suggestion.
Yes. Yeah. So you're randomly like you pick one training set and you randomly roll out like 20 trajectories, and then you say like, okay, this is what I learned from these trajectories. I update my theta on every trajectory, and then I go ahead with the next training sample.
This help limiting the
I'll talk about that. Yeah. So first, let me just briefly talk about policy gradient. So here, so pi is the policy that actually suggests what action should be taken based on the state that the robot is in, and pi theta I say is basically so parameterized policy, which actually takes state and action as an input, and it tells you the probability of what is the probability of taking that action in that state, given the theta values. Okay. Is it clear? So we want to maximize the expected cumulated rewards, same as the problem we saw already. So here, again, same equation. What we are trying to do is we take m trajectories and we want to actually maximize our future rewards. So here we are just considering the future rewards from whatever already has been taken. And basically this B is the baseline. It's average of the rewards that has already been collected. Baseline is is basically subtracted from the reward so that it generates less variant distributions, okay, of the action space. So here, how are we parameterizing this policy itself? Is basically we are just using softmax policy parameterization. I'll talk about how does this look in the like IISc is coming from the feature space. That's what will help with scaling with the space. Okay, I'll talk about what is this feature space in the next slide. And basically here we are taking all the actions. Okay, so you're taking normalized on all the actions. So this gives you a probability value. Is clear? So the idea of the training phase is to get a good parameter theta. And this phi feature that I mentioned about. So in that, the phi prime s is coming from the field itself, the prior that you have, the map itself. And then we are taking this Chronicles delta, which is 0 or 1 based on the action that you're picking. So if you're looking for action going up, then Chronicles delta is 1 for going up and 0 for all the others. Okay, all the other actions. So how does this matrix look, or how does this vector space look? Sorry. First, we discretize the word. Let me just go skip this. And now for feature space, what we are doing is, so this is coming from my word. So here I'm taking uniform feature space, okay, where I'm saying each grid is contributing to your feature. So I stack all the 80 features 4 times because I have 4 actions, okay, and my Chronicles delta is 1 for the action that I'm actually evaluating, and then 0 for rest all, right? And this is my phi SA. Okay, so by the design of the features, now you can actually make it scalable. So this one you're considering every grid still. This is still not scalable, right? So we tried different kinds of feature aggregations. This is coming from image processing again. So you kind of this is the Bayesian algorithm where you're actually like, as you go farther from the center, then your resolution goes on reducing that you're considering for taking an action, right? So what's happening here is these feature spaces are robot centric. So wherever the robot is, the locations which are closer to the robot are taken with higher resolution, and locations that are farther away are taken with lower resolution. Okay, here my feature space is fixed to 24 features. However big my region is, I'm fixed to 24 features. And then I'm not ignoring the features which are farther away. I'm still considering them, but with lower weight. Okay, this is clear. So we tried 4 or 5 different kinds of feature aggregations. These were just like manually designed, engineered feature spaces. So one of them was all grid features, that is uniform features for all the grids. And then we had like 4 feature aggregation where you say like, I draw a line on the right of me and then say like average all the values on the right as one feature and average everything on the top as one feature, things like that. And what we found is basically there were 2 24 feature aggregations we tried different ways. One is uniform 24 grids, one is multi-resolution. And with multi-resolutions, we saw it working much better, like the reward collection was much higher for the same number of iterations of the algorithm. Are you guys with me? I see Rahul. Sorry?
Aggregation thing that have been done in the previous algorithm, not possible to do it in that way. Maybe the computing is deeply.
For the value iteration? But still, in the value iteration, what happens is for every state, you have to go through all the states. Like your computation should go through all the states. Here with policy gradient, you don't have to, because here you're just taking randomly 20 trajectories and then you're optimizing your maximizing your rewards on those. So this is not optimal, of course, because you're taking 20 random samples. So that way, time-wise, it scales better. So we tried running this on like real environments, and these were the trajectories that we generated for sampling. And as you can see, like if we had a budget, or like if there was something, if it was not any time, then I would have actually went and like done a kind of lawnmower along the pattern, right? So here we are trying to do the exploration and exploit whenever you see good rewards around you. So that's kind of the trade-off which is happening here. So you kind of go all across, and then you collect all the rewards, but then you go on collecting the smaller ones. So yeah, here we deployed a custom-built boat to do these sample collections for cameras, and we had a sonar pinger to get the depth of the region and water quality sensor on the boat. And yeah, the waters were beautiful there. Yeah, and basically again comparing with just a complete coverage path, that is a lawnmower path. We also tried comparing it to two other techniques, which is one is basically going to the maxima, and the second one was basically doing some kind of spiral search, because spiral search has been found to be very good technique, and so it's the one which ants usually use to search some rewards. So we tried both of them. I don't have the results here, but I have it in the further slides. How much time do I have? I think I packed too much. Okay, I'll continue and go through it. So one of the interesting features I found is basically putting a multi-robot system with such a sampling algorithm was much easier. Because why I say that easier is because now you have learned parameters, and you copy the same parameters onto multiple robots, and then you let them go into the environment and say you sample now. All they had to do is just whenever they're close by, they had to communicate which are the regions that they visited, and then those they can update their reward map accordingly, saying like, okay, someone has visited, so they're not valuable for me. So here we didn't have to do like multi-robot training or like multi-agent training here, which is more expensive. And also these are trained on very different environments. Like it doesn't have to be the exact environment where we are deploying it. And adding a robot or removing a robot is much easier. If a robot gets spoiled in between, the mission still continues, and then the rewards, whatever we had to get, the others will cover for the one which is not working. So some interesting results here, like here we are comparing again like three different techniques. So this is the R method, and this is the simple divide area and then do the lawnmower path planning or full coverage, and then we are doing maxima search. So you go to find the maxima and do the A-star algorithm to go to the maxima, and then keep doing that for the next maximum. Yeah. Yes. Yeah. So it's basically there's one comparison which I'm still working on. Like we tried the same thing on a learning as a team. So the comparison there would be like, what is the benefit of learning as a team versus what is the benefit of teaming the learned people or learned systems. So that's the difference. Like here you're building a team of learned, already learned agents, but what are the advantages you get by putting a team together and learning together for sampling application? Yeah, that's, I still don't have results on that. Sure. Yeah.
So
yeah,
when these robots are communicating, they only communicate the information of which rewards they always see.
They only communicate the location they've been.
The location.
Yeah.
So no way do the robots know what the other robot is planning to do.
No.
And can't adapt.
No, they don't know. So one experiment we did is basically we tried changing the communication range, right? Here we start with zero communication. That is, there's no communication between the robots. And then we slightly increase to 50% of Dmax. Dmax is the maximum distance in the field. Like this is basically a diagonal straight line, let's say, right? So if we have a communication range of 15% of the maximum distance in the region of interest, how does the coordination behave? And then if we have like complete communication, how does the coordination behave? So what we found is, this is taking like tens of different distributions and then running algorithm on all those distributions and then averaging over all the distributions. So here we found like with minimal communication or minimal exchange of messages between the robots, that is even with just 15% of the Remax, we were actually able to gain a lot more rewards compared to having 100% communication. Yes. Yes. Yeah. So there's also a difference in time, right? Like if it has already stuck there, so it's thinking those rewards are not covered, so it's going there. So 100% didn't work very well compared to a lower communication, because when you had 100% communication, they kind of divided the area into two segments, and one stayed in one location and did like a lot more intricate sampling compared to the other one. But with lesser communication, they were more explorative. Yeah. With more communication, they become more exploitative. So, yeah. Basically, one takeaway from here is, given a region of interest, and let's say you also the communication range for the robot is fixed, right? Because the antenna that you buy gives the communication range. So based on the communication range you have, you can divide the area of interest into smaller chunks and deploy the robots in those. So now you know like what is the if I say I just need 50% communication, so now you have 1.15 times of the communication range you have, you can actually deploy the robot in that bigger region. So that's the calculation you can make, which is very useful for any field deployments. So given a static snapshot of the world, yes, we are able to do this, but I claimed spatio-temporal, right, in my title. So in this example, this is one example I was telling you. We have the action space is constrained to just take 3 actions in the front. Like if my heading is going north, then I can take northeast or northwest are the only 3 actions I can take. So then you see these curves coming in, right? Because you have to, if I want to go back, then I have to take kind of a curve. So now, what if my field is actually changing, something like ocean current or like plankton bloom that is evolving over time? So what we try to do is, we try to build a predictive model which actually predicts how the field is evolving over time. But only using the predictive model, the predictions get very bad after some time, right? So what we thought is, once we have the predictions for a short term, then you can use that prediction to sample from that region and then add your updated map and give it back to the predictor, saying this is your initial state now predict the next step. And then it predicts something, and then you do the adaptive sampling, the one I already showed you, and then you keep doing this, repeating this. And basically, I won't go into the details of the K-node here. K-node is knowledge-based neural ODE. You can look at this paper. This is the work by Tom. He's one of the students that I worked with during my postdoc. So what happens over time? You see this vortex shading data, right? So if I just have one initial state, after 100 time steps, your output becomes something like this from the prediction only, which is not very reliable. So with our system, here the ground truth is on the left-hand side. These colors are looking nice. Maybe it's the color I chose. So ground truth is this one. This is only predictions over time. And then top 2 are using our algorithm for like at t-1 and at next time t. So as you can see, like we are able to actually keep up with the ground truth, like how the ground truth looks like, even with very minimal sampling that we are doing between the predictions. So some quantitative analysis is basically we compared the root mean square of the reconstructions that we did, and with only pure predictions, the errors went on increasing, of course, and with very minimal sampling between the, so 9% of area sampled between 2 predictions, and the second one is 19% area sampled between 2 predictions. They both are doing pretty well compared to the only predictions. And there we are seeing like proper orthogonal decomposition. So in fluid dynamics, if you're comparing, it's something similar to PCA for fluid dynamics kind of thing. So you're just taking top energies or top modes there. And as you can see, like our predictions are actually very close to the ground truth. Okay? And another experiment we did is we trained the predictor only on the vortex shading data that you saw in the previous one. And then we tested the whole system, that is prediction plus sampling, on a data set where actually the cylinder for the vortex shading is moving. So it's oscillating. And we were actually able to even predict pretty well there. But you see these sinusoids there. That is basically of the frequency of the same frequency as the cylinder movement. So still the energies were very close. The decompositions look very good. And we have also tried it on data from NOAA, the ocean current data set. And we seem to be doing good there. It's still work is under review, so we haven't published this yet. Yeah.
For some reason the slide is
Yeah. I'll share again. Yes. Can you see? Yeah. Sorry, I think I was done with the time and also my slides are done. So yeah, we tried on ocean current data from NOAA and it seems to work fine. It's under review. We are still waiting for results on this. And I would like to thank all the collaborators like field deployments takes a lot of effort. So all of them were needed to deploy robots in the water, and then there were times when we had to swim and get it back, and that's too much of effort. Yeah. And to summarize, like basically we like proposed adaptive information-driven survey techniques, which can be used for monitoring environments, which are can be deployed in large-scale environments, and these are also algorithms that are running in real time on the robots. They are deployed in the ocean, and we have tested it on the platform itself. And for doing any large-scale sampling, I think doing some kind of adaptive behavior is very essential, and doing non-uniform coverage is much essential. So I'd like to end at that time. Thanks for the opportunity to come and present. Bye. Any questions?
What do you think, like, in terms of policy does quite well, but do you think like there are other, like, so in terms of, even if I look at it as a like a reinforcement learning,
Yeah.
within that, what are like key areas of improvement?
Basically, one thing is, if I don't have a prior, how do I start with that? And also, basically reward map building, right? Like how do you build this reward map without a prior? That's one thing. And also the comparison between how close the prior should be. That's one thing I have thought of. And couple other things is basically coming up with some bounds that I can tell or claim that this is better than this particular algorithm. That's what would be good to have. Those are the key things I'm thinking about. And I haven't figured out like what could be the optimal algorithm for this. Like maybe if you have any suggestions, I would like to look at it. Like good start, yeah. Cool. Yeah.
Not be modified to include constraints, like suppose the constraints of the power the voting is.
Yes, you can. I mean, but it's very hard problem to bring that in. I mean, in simulation, yes, it's much easier. But the way power consumption happens on a board, it's much different. Like if you're traveling in a straight line, it's much less power consuming than if you want to make a turn. And then those peaks shouldn't trigger something random behavior in the algorithm itself. So that would be a hard problem. But yeah, of course, like algorithmically you can do it.
Like IISc has this very classic maze, like the mouse mazes. Like,
For RL problems?
no, it's like it's a maze, like exactly like a mouse.
Yeah.
Mouse maze. And if now device is very small robots, and it's the time that you get to the center of it. It's a craze in Japan that you won't believe.
I haven't seen that.
Oh, it's
Okay.
oh,
Okay, I should look up then.
that's awesome. Like it's fun. It's better than.
I've seen all the RoboCup and everything, but I haven't seen this maze one. Thanks.
Like second decimal of a second is the difference between like the winner. It goes like
Nice.
it's like Hussein Bolt.
So they have the map?
So they
They know the map.
They know the map.
Okay.
You don't know it a priori, so you can't hard code it.
Yeah.
But before you let your mouse through, you get to.
So I think 5 or 6 minutes to explore the map.
Yeah.
Or I think you're allowed some number of runs in the map. Then
Yeah.
Okay.
use the model to plan it.
So you have a way to build your player.
Yes.
Yeah.
But like it's just so these motion.
So also I don't know what, like how big are these? Very tiny?
These are like
Oh, okay. Those cockroach robots that we see. I don't know what compute is going on. Like,
oh, it's spectacular. Like for example, right? Like
but do they have something like overhead, like external compute that's actually aiding it or not?
Yeah, to the intricacies. But the fact that you don't have to turn like turn an angle, like doing this is a bad thing,
Yeah.
and cutting is a
Okay, yeah.
better approach, or the fact that you should not optimize for distance, but also account for the number of turns. So all these
Yeah,
are
yeah,
like,
Also, there all the dynamics like your state space. State space has all the velocities and your like your velocities come into picture. Yeah, that could be. I should look up that.
fun
Yeah.
YouTube videos.
I don't know this. Oh, thanks.
IEEE mouse something.
I don't find.
Yeah.
Any other questions? I think I am over time. Yes. Okay, thanks. Thanks.
So this is
Thanks. Thanks for the invite. Yeah. And you have beautiful